In this video I will discuss a little bit more about hydraulic cylinders. Here's a simple hydraulic system that contains a cylinder. Hydraulic cylinders are specified by giving the bore size, the rod size, and the stroke. The bore size is simply the inside diameter of the cylinder. That's what the word bore means, the diameter of a hole. In this case it's 2 1/4 inches. The rod size is the diameter of the rod. And the stroke indicates how far the rod moves as the cylinder extends or retracts. For instance, let's retract this cylinder all the way to the bottom and make a mark at the end of the rod. As it extends, it will eventually reach fully extended position. The distance between the fully retracted and the fully extended position is the stroke of the cylinder. Now let's talk about how we calculate the load lifting capacity of a hydraulic system. In this simple hydraulic system, a pump provides a constant flow of hydraulic oil, and if the directional control valve were shifted to this position, the oil would flow through it and down into the bottom of the hydraulic cylinder. As the hydraulic cylinder moves, the oil in the top would be forced out, back through the valve and into the reservoir. If this hydraulic cylinder were required to lift a weight, it is very important to notice that the pressure in this line that's leaving the hydraulic cylinder has nothing to do with the amount of weight that's being lifted. Pressure depends solely on downstream restrictions in the system. And if fluid is free to flow through this pipe, then no pressure would build up in this line because fluid is free to flow. In this red line, however, pressure would have to build in order to overcome the load. Let's say the pressure was able to build to 1,000 psi. If you remember from your high school physics class, pressure acts in all different directions. So there would be 1,000 psi of pressure in all different directions in the bottom of this cylinder. The pressure on the outside walls would try to burst the cylinder open, so we would need to make sure that the wall thickness was sufficient so that the cylinder didn't burst open. The pressure along the bottom would try to blow off the end of this cylinder, so we'd need to make sure that that was strong enough. And the pressure on this piston would try to push the piston up. So let's focus only on the pressure on this piston, because that's what's going to provide the lifting capacity in this cylinder. PSI of pressure stands for pounds per square inch. If there's 1,000 pounds for every square inch, then we will need to know how many square inches of area are on the bottom of the piston. If this was a 2 1/4 inch bore, then we could calculate the area on the bottom of that piston by pi r squared. That's the equation that mathematicians use. But engineers realize that they can't measure radius directly. They have to measure diameter first and then divide by 2. So engineers will adjust this equation to reflect the diameter instead of the radius. And diameter over 2 squared would be the diameter squared, and the 2 also squared, becoming a 4. So this is the equation engineers usually use for area, pi d squared over 4. The diameter of this piston is 2.25 inches, which results in a 4 square inch area on the bottom of that piston. So if there is 1,000 pounds for every square inch of fluid pressure acting on 4 square inches, that would result in a total load of 4,000 pounds of force on the bottom of that piston. So we could lift a 4,000 pound weight. What if, however, the pressure in this line had to build to 200 psi to overcome some restrictions in the line? Maybe this valve is too small, and so as the fluid passes through here there is a restriction. Or maybe the piping is too small, so that pressure has to build to overcome the restriction caused by the piping being too small. What would that do to the ability to lift a weight? Well, this 200 psi of pressure would be acting downward on this piston, but it wouldn't be acting on the entire area of the piston, just on this, because the rod is taking up some of the space. If we were to calculate the area of the rod using the same equation, pi d squared over 4, diameter in this case being 1.125 inches, the cross-sectional area of that rod is 1 square inch. So the area of the top of the piston would be the 4 square inches of the entire piston, subtract out the 1 square inch of the rod, a 3 square inch area. So the 200 pounds per square inch acting on the 3 square inches would result in 600 pounds of downward force on this piston. So with 4,000 pounds pushing up and 600 pounds pushing down, that would mean we cannot lift 4,000 pounds. We could only lift 3,400 pounds. Now let's talk about cylinders that are piped in parallel. You'll notice that the fluid from the pump is split and could go either into the cylinder on the left or the cylinder on the right. And the oil from the top of both of these cylinders could come out and combine and go back to the reservoir. These cylinders are in parallel. The oil from the pump would not build up any pressure because there is no load on this cylinder, and no pressure would build up in order to overcome no load. So this cylinder would extend. Once it got to the end of its stroke, then pressure would be able to build up. And that pressure would build up high enough to overcome the load. And then you would see this cylinder on the right extend. So cylinders in parallel do not operate in synchronization. The one with the smaller load will extend fully before the one with the bigger load will even begin to move. Now let's talk about cylinders that are piped in series. The fluid from the pump goes into the bottom of this cylinder, and as it moves, oil from the top will come out and go into the bottom of this cylinder. And as this one moves, oil from the top here will go out to the reservoir. These cylinders are in series. The pressure in this line would be 0 psi because we would assume free flow back to the reservoir, no restrictions. The pressure in this line would also be 0 because 0 psi is needed to overcome zero load on this cylinder. This line would have to build pressure because it's going to overcome a load. The pressure would be pushing on the bottom of the piston. If that area were 4 square inches, 1,000 pounds for every square inch on 4 square inches would result in 4,000 pounds of force, enabling us to lift a 4,000 pound load. What about the speed of cylinders that are piped in series to one another? Well, a hydraulic pump provides a constant flow. Let's say in this case that the hydraulic pump has injected 66 milliliters of oil into the bottom of this cylinder. That's 4 cubic inches. As this begins to move, oil will be piped out of here into the bottom of this, and as this begins to move, oil will be piped out to the reservoir. Let's make a mark at where this piston is and this one so that we could see which one will move further. If 4 cubic inches of fluid go into the bottom of this, and this happens to be a 4 square inch area, then the piston will move 1 inch. But because the area on top is smaller, only 3 square inches, because the rod is taking up some of the space, only 3 cubic inches of fluid will go out. Notice 4 cubic inches of fluid went in and only 3 cubic inches went out, which means 3 cubic inches of fluid go into this cylinder. And 3 cubic inches on this 4 square inch area would result in this one moving only 3/4 of an inch. So notice 4 cubic inches went in here to cause 1 inch of motion, and only 3 cubic inches of fluid went in here to cause 3/4 of an inch of motion. So you'll notice that the cylinder on the left, the first one in the series, moved farther and faster than the one on the right. Now you'll also notice that because 3 cubic inches went in here, and the area on top of this was only 75% of the area here, because the rod is taking up some of the space, we would measure only 75% of the fluid coming out here. So 4 cubic inches of fluid go in here, 3 cubic inches come out and go in here, and only 2.25 cubic inches come out and go to the reservoir. Now let's take the load on these cylinders and place it on this side instead of this side to see what happens. Again, 0 psi will build up in this line because we're assuming no restriction in the line that goes back to the reservoir. What about the pressure in this line? It certainly can't be 0. Pressure will have to build to overcome this load, this 4,000 pound load. If that area is 4 square inches, well, we will build 1,000 psi of pressure to overcome the 4,000 pound load. 1,000 pounds per square inch on 4 square inches would be able to overcome a 4,000 pound load. And if the pressure in this line is 1,000 psi, well, that would measure 1,000 psi up here as well, which means there's 1,000 pounds per square inch pushing on 3 square inches of area, resulting in 3,000 pounds of downward force on this piston. So that means there would need to be enough pressure build up here to provide at least a 3,000 pound lifting force on this piston so that it could start to overcome this load. And if this area was 4 square inches, then 3,000 pounds divided across 4 square inches would result in 750 psi of pressure. Isn't that interesting? So when the load was on the right side, only 750 psi of pressure needed to be developed to overcome this 4,000 pound load. When the load was on the left side, 1,000 psi needed to be developed to overcome the same load. It's also interesting to note what's happening across this piston. 750 psi of pressure going in, but 1,000 psi of pressure are coming out. We've essentially used this piston that had no load as a pressure amplifier. Now let's take a look at what happens to the speeds of these cylinders. Before, we noticed when the load was here, this one would move faster and further. Is that still the case when the load is here? Well, if 4 cubic inches of fluid go into this, then fluid would come out here and go out to the reservoir. And if we were to mark the positions of these, we would notice that this one would move 1 inch because 4 cubic inches went in, which would cause this to move 1 inch. And because this rod is taking up some of the space, only 3 cubic inches of fluid would go out and go into the bottom of this, moving it only 75% as far. So no matter which side the load was on, whether it was on the left or on the right, the cylinder on the left moved faster and the cylinder on the right moved slower. And the speed difference depended on the ratio of the area on the bottom of the piston to the area on the top of the piston. In this case, it was a ratio of 3 to 4, which is why this one moved only 3/4 as fast.